Next, we're going to be talking about algebraic properties that regular expressions have. So these are things that apply for regular languages, but I'm going to describe them in terms of regular expressions. So keep in mind the regular operators. I'm just going to describe them in terms of regular expressions. So algebraic laws for regular expressions. So let L, M, and N all be regular expressions. Which, remember, each one of these has a corresponding regular language that it describes. So you can think of these just as variables that I use in the regular expression that represents a regular language. So in fact, sometimes when people talk about regular expressions, they'll often use the term regular expression with regular language almost interchangeably because they mean effectively the same thing. But more technically speaking, each one of these has a language that it describes, and that is the regular language in question, as we established previously when we established Kleine's theorem. Remember that in Kleine's theorem, we established that every regular expression has a corresponding finite state automaton, and previously we had actually also established that for every finite state automaton, that you could actually construct a regular expression that also is describing it. So it means that there's an equivalency there, hence any regular expression actually is regular. So I'm going to justify each one of these, and you'll see quite quickly that we end up with a bunch of fun properties. So one thing I should mention before we get into this list is, remember how I talked about how the regular operators are closed operators? So meaning that union, star, and what else? Concatenation. These are all closed on regular languages, meaning that if I give you two regular languages, I apply these operators, or just a single one for the case of star. If I do that, I still end up with a regular language. You might ask, Dan, how do I prove that's the case? Now that we have Kleine's theorem, this actually becomes incredibly simple to do. Because if two languages are regular, then that means that each one of them has, because of Kleine's theorem, regular expressions, right? Their concatenation as a regular expression, is that regular? Yeah, it is, because remember, each one of the pieces is regular. Their union has to be regular because that regular expression has a corresponding DFA. And you can make the same argument akin to this with star and concatenation as well. So you actually get the closure properties almost for free. Their proofs are effectively just 1 to 3 lines long, and effectively boils down to, well, if like L and M are regular expressions, then they are regular, right? So like, or vice versa. Then you use that bits and pieces to just say, hey, look, well, this, where I take L and M, that result is a regular expression. By this theorem, it has a corresponding DFA, hence it's regular too. So first we have the commutative law for union. So that means that L plus M is equal to M plus L, or union. Well, if you're not convinced by this one, just simply write out what those would be in terms of their languages and what the union operator is. If the union operator is commutative, then most certainly its regular expression counterpart is too, right? Again, we have another one, distributive property. You're going to find that almost all of the things I just described here have very similar reasoning to them. So if it applies for union in the set theoretic sense, it most certainly will apply here. So both L, or I concatenate L with M or N, this is the same as me writing M concatenated with M and L concatenated with N. So L concatenated with M, L concatenated with N. And of course, you can write it the other way around too. And M plus N concatenated with L is the same as writing M concatenated with L or N concatenated with L. So not very terribly surprising. So I'll let you think about this one. So if you're looking at this and you're like, okay, Dan, why is that the case? Go back to the definitions for these things. So if you want to establish this, show that every member of this is the same members here, right? So this is the same language as this one. So you can do basic set theoretic arguments using definitions of these operators. Okay, let's see associative property. Associative law for union. So the associative law for union works like this. It just tells you how you can lay out parentheses. So if I have L or M, or L union M, then parentheses, this is the exact same as if I were to put the parentheses following L, so it groups M or N. Next, we have the same idea, associative property or associative law for concatenation. L concatenated with M concatenated with N. This is no different than if I concatenate L with the result of concatenating M and N, or let's write it like this instead now. If I do the concatenation between L and M first before I do it to N, these are the exact same thing. If you're not convinced by this, pull out the definition of what concatenation is and see what the resulting languages would be in each one's order. So we got identity. We've touched upon this actually when we were doing our example, when we were applying the construction from a DFA to a regular expression. Identity for union. So if I take the expression for the empty language, I union that with some regular language. It's no different than if I write it like this, and it's also the exact same as if I just wrote the language, because remember, it's union, right? This is the empty language. Well, that's what the expression for this, so that's the language of that expression, is just the empty set or empty language. Union with something. Now that's not, this guy's not going to contribute anything. So whatever is left here is going to be whatever's left, right? If it was empty, then it's just empty, right? Okay. Let's get an identity for concatenation. So if I have the empty, so the expression for the empty string, and I concatenate that with L, this is no different than if I wrote the language first, and I concatenate it with the empty string, which this is, of course, just the language itself. You might ask, Dan, why is that the case? Well, remember, the definition of concatenation over languages is where I take each string and I concatenate it against the strings in the other language, right? Well, this one only has one string in it, the empty string. And the concatenation with the empty string with any other string that has one or more symbols, what kind of string is it? It's just the string itself, right? So I go through every one of the strings in one language versus the empty string, concatenate it one after the other, it's just going to end up being the same language, right? Now next we have the annihilator. Dramatically, the annihilator. The annihilator. I didn't come up with this name, by the way. It's just a pretty dramatic name. the annihilator for concatenation. Again, another one we touched upon in the past. Annihilator for concatenation. So this is where if I give you the empty language, the expression for it, I concatenate that with a regular language, namely its regular expression. Then that's the same as me writing this, which this is the result is going to be the expression for the empty language. Why? Because remember, this is the empty set or an empty language. I have no strings. There is no strings to concatenate with in one of the sets. So it means, or languages. So I have none versus something potentially, but the definition of concatenation is that I take each one of the strings in one and I place it in a concatenation with the other, and the resulting language is that operation with each one. But there's none in one of them. So that means that there's none in the result. So that's why it's like this. So here's another one. So imagine I have two of the same languages. I'm performing union operations with them. If I take the union of a language with itself, what happens? What happens? What happens? Well, most certainly it doesn't introduce any new strings, right? So L union L, or L plus, or L or L, is going to end up being L. Nothing too terribly surprising there, right? Again, if you're not convinced by that, just pull out the definition of what union is. So here's some more laws. So these ones all involve star or closure, whatever you'd like to call it. So if I have L, and I perform a star operator on L, then I star the result. This is actually the same as L star. So that's the first one. The next one is if I have the expression for the empty language, if I perform star on that, this is actually the same as me writing the expression for the empty string. 3. The expression for epsilon star, it's just the expression for the empty string. If I have epsilon and some language for this expression, and I star this, this is no different than if I wrote down L star. You might ask, Dan, why is that the case? Well, notice that it's either I can take L or I take the empty string. I can do this 0 more times. Suppose that I do take it 0 times, this. Well, I can take this whole thing 0 times. I could have also made this choice of not including it at all, right? But that's no different than if I just didn't pick any of these, right? But this option permits me to just simply pick nothing, which is the same as not taking L at all. So notice that this epsilon here is absolutely redundant. You can always just drop it out of there. Because star gives you the option to not pick any of them, right? Now, a couple other remarks I want to make. It involves writing one or more, and we've touched upon this actually previously. Is what do we do with one or more? So star is really useful if I want to say 0 or more, right? If I want to write 0 or more, star is helpful for this. I touched upon this before. We can define L with the exponent being a plus to be L or LL or LLL and so on. Where we have the following properties or laws. So you might ask, Dan, why would I need this plus business? So very often if you want to concatenate and then you allow an option, the plus is a substitute for this whole thing, because you're always going to force there to be at least one. So if you're looking to kind of make your expression somewhat more compact, some will allow this plus in the exponent as opposed to a star. So if I have L plus, this is actually the same as me writing L concatenated with L star, or if I have L star concatenated with L, as I just suggested. This is the exact same thing. We've actually seen examples where we had regular expressions like this. Now we have L star. If ever I want to get back L star from L plus, I could take union with the expression for the empty string. So those are the nice laws that we can talk about when we deal with regular expressions. Notice that they have their corresponding regular languages, and you can look back at their definitions in relation to the regular expressions to help you establish or prove them. So we also touched upon at the beginning how these closure properties happen to be true for the regular operators because of the equivalencies we've established in the past involving regular expressions and deterministic finite automata. Wasn't that fascinating, Miss Kitty? Wasn't that fascinating?